Okay, so today I'll be talking to you about promises and evaluations and risk and failure of so-called foundation models and the generative models that are built on top of the foundation models. Foundation models may sound very, how do I say, very, like an advertisement and very flashy. The way we want to define it, that these are different from the task-specific machine learning model. These are models that are first pre-trained on a large set of unlabeled data set. And then it could be, and that training can happen using self-supervised learning or some form of unsupervised learning. The model then learns generalizable and adaptable data representation, which can be used for multiple different downstream tasks with the minimal or almost no fine-tuning. So this kind of sets them as a different paradigm from the task-specific machine learning model, because now we are not starting with a task-specific data set, rather we are talking about a domain-specific, very broad, large-scale data set. And so the foundation model term was not coined by us, but was coined by Stanford HAI, I think in 2021. It's getting a lot of momentum and popularity, also criticism, but for the context of this talk, we'll stay with this definition of foundation model. Just a disclaimer, though these models are built on top of the transformer deep neural net architecture, but we would like to generalize the definition of foundation model a bit, and we will just say that as long as we have an expressive neural network architecture that the foundation model is built upon using this paradigm of training, we'll call it a foundation model. Now, why I'm starting my talk with the foundation model, I guess everybody almost in this room now knows about Stable Diffusion, about DALL-E, CLIP, ChatGPT, and then we are already seeing the Twitter, conversation around GPT-4, that how many parameters it would have. So if any of you don't know about this, so these models, all they fall around this category of foundation model, either in image generation or language, or in image-to-image captioning, where we need to train a model on image-text data pair. And in each cases, they are trained without any labels. And then one model, one foundation model pre-trained using a lot of data, a model that has a lot of expressivity, could be into billions of parameters. And then that same model is now being fine-tuned in many different tasks. And that's being the trend, and we have seen while the trend started with language, now we are starting to see that the trend is now kind of impacting other fields, many scientific and enterprise applications such as speech, finance, as well as chemistry and biology. Cecilia showed, and I think many of the other speakers would also show AlphaFold. It's kind of I would say foundation model, because there also MSA is being used, which is kind of capturing the sequence similarity, and that's taking its scale to learning from a large volume of data. So I will be showing you some example of these foundation models specifically designed for molecules. And when I say molecules, I mean both small molecules as well as proteins. The first question we'd start with, that why do we need such models for molecules? Well, one argument there is that though there are for years of research for ML for molecules, we do have quite some benchmarks, quite some data sets, but still if we just look into the number of molecules that are possible, here I'm talking about small organic molecules versus the number of molecules that has been characterized, we have been able to characterize a very tiny fraction of the entire molecular world. And then in many cases, like recently we have seen in COVID, we are experiencing new situation where we do not have a lot of data set to accumulate, to annotate, and then train models on top of that. So basically we need to rely on broad data, and if we can come up with models that can learn from this broad data and we can repurpose that model that can be used for, let's say, SARS-CoV-2 inhibitor design and stuff like that. So that will be really useful. And finally, we know that there are certain rules in chemistry. There are certain principles for biology. If there are such rules, it would be nice to have one domain-specific model, let's say one for proteins, one for small molecules, and maybe one for all of the chemical entities in the world. And then we can get from there to learn really about the domain, about the knowledge, about the rules underneath it, rather than trying to come up with better and more performant machine learning model. So this is, I think, is more driving force rather than trying to come up with very performant model, trying to see that instead of infusing physics into the model, if the models can infer some physics on their own. So I have tried to break my talks into a few parts. And so the first part, I will start to show that such models, such foundation models for molecules, indeed could be used for property prediction and generation. Since I showed you the slide in language, I would start where we are modeling the molecules using the language as a modality. So it could be protein sequence or it could be chemical smiles. So these models that, as I mentioned, that we want to make them learn the language of chemistry and biology, and by language I mean here the grammar, the rules, and from data itself, and see that if they can help us with the property prediction, different property prediction, or molecular design task. And we call them as MolFormer. We were thinking what to call them, if it's a family of molecules that all fall into that category of foundation model trained by using self-supervised or unsupervised training paradigm. And we thought, MolFormer sounds simple and sounds good as well. So let's go with that. Over the years, we have been looking into this paradigm of training models. We do have quite some work there. I won't be able to go over all of them. But like I mentioned, our goal is to learn a common representation, a common latent representation for chemicals or for proteins, and then use that for different product property prediction or design tasks. And the recent addition to that family that we just published last month is called MolFormer Excel. Again, Excel, because this is the largest we have so far, doesn't mean that that is going to be the largest or it's going to stay large forever. So it's a model built on using transformer deep neural net architecture. Transformer uses self-attention, so these are different from LSTM, because in transformer we are using more like context-dependent learning. So given let's say a query, which is a token within a model, it could be a particular chemical atom or it could be a protein sequence, and we also have another one that we would be the key. So we want to see what are the relation between these two. So rather than learning to predict what's the next token, which is typically being done using LSTM as we do language modeling, transformers bring a very different way of learning, which is important as we are trying to learn not only what comes next, rather than we want to learn more of the global context. Most of the transformers are being trained using something called mask language modeling. So basically we mask a part of the sentence or a sequence, and then the model is asked to predict what should be in that mask section. So that's mask language modeling. Now specifically speaking about MolFormer Excel, we train this model over 1 billion of chemical smile string. This is different because if we are talking about, let's say, the benchmark QM9, we are talking about 134K molecules. So from there, we are really scaling up in terms of data. And also, we are using a typical transformer architecture. So it's about 50 million or so parameters. So it's a good expressive neural net to train with. Though I come from industry research, I come from IBM research, you might say, okay, you can do all of that because you are sitting on hundreds to thousands of GPUs. Yeah, that's true, we do have, but it's not available for us. All of that is not available for us. So in this case, we came up with a way to train it using only 16 V100 GPUs. And my team member just confirmed that we can also do the same amount of training now with some tricks here and there in 4 GPUs as of this morning. So how do we do? Yes, go ahead.
Where did the billion smiles come from?
Sorry?
Where did the billion smile strings come from?
Very good question. Thank you. Sorry, I missed that. It came from Zinc and PubChem. Zinc database and PubChem. So publicly available database. And there are more. I think we don't need to be constrained by that. So that was just the starting, but 1.4 billion was not too bad. And I will show you some scaling experiment that, what happens if we go less, not more. We are going more now, but those results are still not in, So how do we train using 16 V100 GPUs? So of course, we needed to do parallel training, something called adaptive bucketing, where we tried to restrict sequence length as we were doing the mini batch training in training the transformer model. But more so, like I mentioned, that when you are doing using the attention mechanism within transformer, it has a n-square complexity because we are trying to come up with learn the relation between each pair of tokens. There is a more efficient way to do that, what is called linear time attention transformer, which is basically reduces the complexity of computation from n-square to linear. And finally, we use something called relative positional embedding. So if you see that in transformer, what we have is something like a token embedding or like chemical character embedding, but on top of that, there is something that is grayed out here, is called position encoding. So it is important for a transformer, as we are feeding a sequence, that what is the location of that particular token within the sequence. Now we found out that the standard way to do is show by feeding the model absolute positional encoding. So let's say if it's a CCC, NCO, maybe a wrong molecule, but let's say that then we are talking about 1, 2, 3, 4, 5, 6. So you can feed just that as a one-hot encoding, or you can just train encoding parameters on top of that. But we found that that doesn't help the model to learn much. Rather, if we try to learn the relative position, so for each token, we are trying to learn that how it is positioned within the all other tokens or in the context of all other tokens. So that's something called relative positional encoding, and it can be done with a very simple trick where we do a position-dependent rotation as we are trying to estimate the attention or train the transformer model. So with these few things, when we train the model, we found that the model actually performs very well with minimal to no fine-tuning on 70 plus molecular property prediction. And that includes the popular molecule net benchmark, some of the one from therapeutic data commons and so on. More importantly, which I think would be interesting to this audience, is that we see that in that, as you see that here we are not using any label as we are training the MolFormer XL. As we look into the latent space learned by this MolFormer XL, we see that the molecules are separated according to their taste. Like if a molecule is bitter versus sweet, they are well separated in the space. So meaning by pre-training on this large amount of data, the model is starting to learn something that is very intrinsic to the chemicals. And it doesn't even need to have access to such labels. So that's really interesting to us, and I will go on to that even more later on. So this is I think it was our first figure in the paper, and then we moved into the supplementary. But just to show how the model does in comparison to some of the state-of-the-art models, graph-based and geometry-based. When I say geometry here, I'm not talking about something as sophisticated as SNET or DimeNet. That comparison would come later. But here in graph, it's just 2D graph neural net. AFP is the attention fingerprint to one model. 1 to 3 GNN is a k-order graph neural net. GC is just simple graph convolution. And in the geometry-based, what we have is a model trained on Coulomb matrix, deep tensor, that's an extension of that, and then message passing neural net where the edge information includes the bond distance. And as you can see that, 1 to 3 GNN, which is a more expressive form of graph neural net, it does actually very well when we compare MolFormer XL to that. But 1 to 3 GNN is more, the computational complexity is much more because we are talking about k-order graph neural net there. And MolFormer XL is much faster to train and much faster to infer because it operates on text strings. And overall, on QM9 benchmark, the average MAE for MolFormer is much lower compared to others. But is that it? No, that's just the beginning, because we thought that no other language model typically trained on chemical smiles do experiment with QM9. So we just wanted to see that how bad our model can do, because for quantum mechanical property prediction, we do need accurate 3D conformer information. So it's kind of nice to see that a model that had no access to such information can still do well on such tasks. But now to remember, our goal is to find a model, a foundation that is generalizable, that is task agnostic, and we can easily adapt it to any downstream task with a small amount of fine tuning. So here I am showing you the result of when MolFormer XL is fine tuned on each of these property prediction tasks. Some of the top figure is on classification and the bottom is on regression. And again, you can see that the model now actually shows its benefit. It's very generalizable. So that's really an advantage. And so if that's the case, then one application we immediately thought that the model could be used for virtual screening. So it could be like if MolFormer has so much knowledge about chemical smiles, then we can use it as a document retrieval system. So anyone can use the model as a backend database and then query it for a given molecule. And what this interface does is it uses the MolFormer embeddings as a backend and retrieves the k nearest neighbor for the query molecule. If I have time at the end of my talk, I will show you how it works. But for now, I'll just keep it. And then we started looking into how if it's good on property prediction, can we use it for design or generation? So we tried to create something like GPT. So instead of property prediction, now we have a generative pre-trained transformer, which we call MolGPT. So basically here it is now doing the token prediction. So the goal is that if we give part of the chemical string, the model will complete it, and the decoder architecture relies on the MolFormer Excel architecture. And although this is, you can always say that that how good the model is, that we have some metrics that when we are looking into the chemical validity of the generated string, uniqueness and novelty, these are metrics that has been used by many of the researchers who have been actively working on molecule generation using deep learning models, including Rafa, who is sitting here. So so these metrics, of course, they have their limitation, but they are good for a sanity check. Of course, like the final test or a Turing test of a generative model would be if we can discover new molecules, and I'll get into that. But this is a good sanity check. At least we know that the model is not worth throwing out. Any question from the audience so far? Okay, if not, I'll.
Question. So, in the QM9 results you showed, MolFormer was pre-trained on
1.1 billion and then fine-tuned. And we also have in the paper, we show if it was frozen, so we didn't do any fine-tuning, how bad it is. But the result I showed you, then it is fine-tuned on 80-10 split on QM9 data.
So fine-tuning means you just leave some parameters variable.
Exactly, yeah, and we also have the results.
Supervised training on QM9.
Yeah. Mm-hmm.
Also regarding the QM9 results, do you have any insights why the smile-based approach is so much better than the geometry-based approach? Is there any obvious?
Yes, I will get into that. That comes, yeah. So that was actually the question. I think though we didn't expect that that our model do the best on QM9, there is no reason. But we were surprised to see that why even it's doing to some extent well enough. And we looked up into that, and we have some answer to that will be covered in the next section of the talk.
But then, QM9 is just basically, one particular geometry for each molecule.
Yeah.
And I imagine that if you, say, leave a few hundred parameters and you just optimize them, you can always represent it with just smiles information. So because your model is very large. Right?
Yes.
So, but if you take, something like conformational ensemble.
Yeah, like MD17 or something.
Yeah. How the parameters change, right? Mm-hmm. They change a lot, right?
Yeah.
So that you cannot describe with your model.
We do think it is possible to describe because we do have some initial results supporting that. Because I will get into that what we are capturing or what MolFormer is capturing through the lens of attention is some spatial distance information between nearest neighbors in a graph, though it doesn't have access to that.
But what is your then input if you want to do confirmations?
If we want to do confirmation, right now we are not using, so confirmation, when we are using the QM9, we are still using smiles. So if we are doing confirmation, we'll still use smiles, right? But what we'll try to see that what is the uncertainty or what is the spread of the prediction, right? In a sense, that would be capturing as the property changes with the conformational diversity. So that would be the very first step. But when I'm saying all of this, that doesn't mean that we can go without geometry. What I'm trying to say that geometry is not always available, and it is good to have, or it is useful to have a common foundation and model which is trained on chemical smiles representation. Maybe something UPAC or INCHA you would be even doing even better. I don't know that, but it's good to show because if we learn a model, let's say on QM9 or MD17, those models we won't be able to generalize them, right? And we won't have conformational data for all of the possible molecules in the world. So it would be good for us to still have a foundation model, and we are also looking into, I'll get into that, how we can use smiles encoding on top of three-dimensional encoding, geometric encoding. I hope I will have time to cover that. Okay, so if we go back a step, so we talked about MolGPT model, which can help us creating new molecules, right? But what we want at the end of the day is not just a new molecule, but we want a molecule that is useful for some purpose. Again, folks like researchers like Rafa and et al. Have done wonderful work in that domain, and they have created the very first set of benchmark and paradigm of how to come up with such models. Here, what I'm trying to say is that there are many methods to do this kind of controlled or property conditional generation, and I'll be trying to talk to you about a specific way one can generate design property condition or attribute conditioned molecules. So, given a set of properties, if you specify those properties to the model would output a molecule that is consistent with the set of properties. So we can use MolFormer as a starting point, and once as we know that the MolFormer has good enough predictive power that it can cluster different molecules in different space and keep the close ones together, then basically we can come up with an algorithm given a set of properties. The model can accept the set of molecules that are consistent with the given properties and reject the ones that are not. And if we formalize this algorithm in a mathematical fashion, so this is how we can do it. So in this case, you don't have to start with a transformer-like model. We have an encoder and decoder, and in this case, they were LSTM encoder and decoder. And once we have such a trained model, what we can do is then we can train some property predictor using the latent space that has been obtained by training the generative autoencoder. And we can also model the posterior that we have learned using an explicit density model like a Gaussian mixer model. And our goal here is to come up with the P probability of X given A, where A is the attribute and X is the sample that we want to generate. And you can write it in this manner, right? And what we don't know here, we have P of X of Z already if we have a trained autoencoder. But what we don't have is P of Z of E, that is the probability of a latent vector given an attribute specification. So we can further write it in complying to base formula like this, where Q phi Z is the explicit density model that we have trained using the posterior of the model. And that can be written as like this. So we can take the Q phi, the posterior out, and then it's just going to be the probability of a number of attribute classifier or predictor that are trained using the latent vectors. So basically it boils down to something like a rejection sampling approach, and we have shown that we can use such rejection sampling approach once we have access to trained latent space of molecules, be it peptides or be it small molecules, and a set of property predictors. So given that property predictor and access to the latent space, then one can use the guidance from the property predictor and perform this rejection sampling to identify G's or latent encodings that are consistent with the property, and then pass it through the pre-trained generator and get access to the generated molecules that are consistent with the given properties. So this was something that we did in 2021. That was when we were going through the COVID pandemic. I mean, it's still not over yet, but at that time it was peak. And one step we took that, if we can use such algorithm to design, let's say, SARS-CoV-2 protein inhibitors, because we didn't have a lot of data by then, by like beginning of 2020. I'm talking about February or March, because this website went live on April of 2020, where we open source 3,000 novel chemical molecules that are designed by this algorithm, which are and also are likely to show inhibition against some SARS-CoV-2 protein targets, and it's all available in open domain. So we have shown you that it is possible to design molecules within few days just using historical data. In this case, what we did, we took pretrained protein embeddings, pretrained small molecule embeddings, and then predictors that are trained on the protein ligand binding affinity data. And then we use this binding affinity predictor as a guidance to come up with new molecules using the class algorithm that I mentioned before, which are consistent with high binding affinity to the desired protein target, but low affinity to all other. And then you can include more and more properties as you want. Yes.
Question, just to make sure I understand the claim that you're making, that you can take an embedding of a protein, take an embedding of a molecule, and with no experimental data of any molecule binding to that protein.
No experimental data of any molecule binding to that protein. Yes, that's true.
And the claim is that then you can have a usefully high hit rate of a molecule that I generate from that latent space and say
that is the claim.
Going to be higher than, like, what kind of hit rate are you getting?
Okay, so we haven't done experimentation on thousands of proposed designs because it's just so expensive, and all of this was done during the when we were in COVID, right? We were working with Enamine, and then Enamine being located in Ukraine, they also had their own share of other problems, right? So, but what we did here, we picked 4 molecules for 2 different targets, so 4 for each. 4 for main protease, which is very similar to some of the targets that are covered in the previous protein ligand binding affinity data, right? And then we also took spike protein. And another one, I think, was NSP15, for which we still don't have any experimental validation. We are working on that. But for spike was not so much covered. Spike RBD was not so much covered in binding DB data that we used to train our protein ligand binding affinity predictor. What we found that, in both cases, we found 2 molecules from each of the 4 for each target, right? They showed micromolar level inhibition. So now you can ask that, is micromolar inhibition good? For hits, they are good. For lead, no. We need to do further optimization on top of them. But we still feel like this is a good kind of starting point to show that this is plausible. And one other thing I want to mention, the question you asked, that these are the molecules that we have synthesized. These are the designs that were synthesized and tested. What we found that for like this, I'm really struggling here with the laser pointer, but Gen 727, this one showed not just viral replication inhibition on the original Wuhan sequence, because that sequence is being used only during the inference, right? But what we found that Gen 727 also shows broad spectrum inhibition to all the way up to Omicron. This work was done in collaboration with researchers from Oxford University and Diamond, particularly Professor Dave Stewart's group, and they were also pretty, I would say, impressed and amazed to see. But again, because we are using the protein embeddings, we have a feeling that the model also captures the relationship between different sequences, so it shows some broad inhibition activity. On the left, we show the demonstration on antimicrobial design. So in that case, our domain is peptides. Same story, we found that we sent in that case 20 peptides to lab for synthesis and validation. 5 of them showed antimicrobial potency, and 2 of them came up with broad spectrum potency, low toxicity in vitro and mouse model, and also low resistance onset. And these results have been published, or they are available in arXiv. So this is good that we do. Again, the problem of molecular discovery is not solved, but we are getting into some tools that can probably expedite the process and make the process more efficient. And we do not need to do many trial and errors. And but so far we have seen that the model does good in terms of prediction. They can be useful for predicting many properties. They can be used for defined design tasks. but someone from the audience already asked that what's happening in this model. So we'll try to open this large 43 or 50 million parameter model and try to see something, if there is anything meaningful for us out there. So we'll go back again to the MolFormer Excel model. So first we are when we talk about emergent behavior is defined here as a behavior that is not seen when the model is trained on smaller amount of data or the model is not expressive enough. But as you scale, either using data or more neurons, more parameters, or a combination of those, you start to see either some performance gain or some behavior that you didn't expect, that was not even considered in any of the fine-tuning or pre-training tasks. So here, what we are looking at, you can see that on the top 3 rows, we are showing that how MolFormer Excel, our 46 million parameter model, when trained on less data, how they perform. So you can see that in most cases, we do see a gain in terms of performance as we train on more data, right? And then we have MolFormer base, which is basically half of size of MolFormer Excel. Data remains the same, the model goes in terms of size, half. So instead of 12 layers, we have now 6 layers. And then you can see that significant performance lowering in some tasks, while close enough in some other. So meaning that that as we scale in terms of data and model size, these models are learning to be more useful. And we also were asked by the reviewer to compare with the SNET and DimeNet, and was predicted that this model would be 1,000 or even more, order of magnitude worse. But we found it was like about 7 to 8 orders of magnitude worse than DimeNet, which are models, which of course SNET and DimeNet, both they have very sophisticated architecture. SNET uses the continuous convolution, DimeNet tries to model the directional information by trying to model the angles. We are not doing any of that, just using smiles, but trained on a large volume of data, and it's good to see that the model is not that far behind. And it is possible that if we use some amount of chemical 3-dimensional information, the model can do as comparable to those models. And then GeoMGCL and GEM here are some pre-trained model, if I recall right, which are doing the same sort of pre-training, but they are using geometric information during pre-training, and MolFormer Excel seems to beat them on different regression tasks. Now, finally, so we know that we have heard enough good thing about the model, but what's happening there? So we started to look into the attention map and tried to see if there is anything it is learning that is important about geometry. So what I'm showing you in this table here, the correlation between the distances between different atoms, and we categorize this distance as short. Short is mostly capturing the bond distances less than 2 angstrom, medium 2 to 4, and beyond 4 is long. What we see is that the model, MolFormer Excel, is capturing these medium distances very well. So meaning that the model is starting to learn something about spatial geometry and is capturing this k order or nth order interaction between different atoms in a molecular graph. So that is probably the reason that it is starting to do well on some quantum mechanical tasks. One snapshot on a specific molecule, and we have several others in the paper. So here what I'm showing you here is the bond connectivity matrix and the 3D distance matrix of the chemical, of a particular chemical from QM9. Remember, we didn't have access to the 3D information in the MolFormer Excel model training or inference. And what in the bottom we are showing here is the attention with the rotary embedding. And you can see that the attention map with the rotary embedding is capturing, is like reminiscent of this bond connectivity and distance matrix within different pair of atoms within this molecule. And we saw this pattern again and again as we were manually inspecting this attention maps and their correspondence with the distance matrix for many molecule. So in a sense, we think that it is by being pre-trained on this large volume of chemical smiles, it is starting to learn relationship between different functional groups, and that is probably helping it to learn to be useful in any different tasks, including quantum mechanical.
Yes? Quick question. Sorry, yeah. I'm really bad at thinking in 3D. Is there sort of a second nearest neighbor story here?
Yes.
Would this be sort of, you're calling it 3D distance matrix? but it also might be just second convolution.
Not necessarily all of the time. So sometimes they are not connected, although it's written that, yeah. So sometimes they are not. It could not be connected even by the next neighbor. In many time it is. That's why we are showing the bond. And of course, most of the attention when you see the really, really dark black, there, those are those include the direct interaction and the second nearest neighbor interaction through bonding, right? But the ones that are light gray, those are not. And we have also seen it is in many, in some bigger molecules. For QM9, most molecules are small, right? But for bigger ones, we also see that, those are not directly bonded or not, nearest neighbor through bond. Yeah.
Yeah, I was going to say the real test would be a really big molecule or
yes,
peptide or something.
Yeah.
Really far. So do you see that if they're really close in 3D space, but really far in graph space, that you actually get a correlation between or on the attention?
I would be really, factual here. So the task we have looked into, right? So some of the tasks like, HIV activity prediction or blood-brain barrier prediction, those tasks include some molecules that are longer. We are now looking into polymer because that would be the next step to see that if that's happening in there would be more meaningful. But so far for organic small molecules, we see that the attention captures something that goes beyond next nearest neighbor and the one that is next to it. Yeah. Mm-hmm. Like this is one case where we are not showing you the attention results, but these molecules are from flavor DB and not necessarily all of them are as small as QM9. There are some of them that are, the beta testing like quinine or things like that, they are big enough. And what here I'm showing you that the TSC projection of MolFormer embeddings of these chemicals, and we didn't have access to any level, but you can see that there is some kind of separation emerging within the embedding, although it was never trained with such test level data. So I won't say we have understood everything, but it was kind of interesting, and I think we have a lot to learn, a lot to experiment with such models to see how can they even be useful. But MolFormer Excel is not alone. Us and several others have seen, particularly I think Mohammed and also Facebook Meta team who have trained the ESM1B model with the protein sequences. It was found that when you train at scale, the model, even though trained on sequences, can learn about contacts in protein structures. Here, in the case of peptides, this is a peptide generative autoencoder, and what we have plotted on the left is distance in the latent dimension learned by the generative AE, and y-axis is the evolutionary similarity between different sequences. So we do see when a model has learned enough, the loss is low, and the model shows good amount of predictive capacity. We do see that there exists some kind of anti-correlation between evolutionary similarity and the distance in the latent space. And again, that is the meaning that the model is learning something about evolutionary similarity without having access to MSC information in this case. ESM1B showed one further step where they are able to learn predict about contacts and secondary structures in protein sequences, while the model was only trained on sequence data samples. So how much time we have? Okay, 6 more minutes, good. So now that we have seen that this sort of foundation models also start to show interesting emergent behavior, we started to ask the question that does that mean that we have to train one model from scratch for each domain? Because it may or may not be possible, and like you mentioned that, where is the end? We have a model trained on 1.1 billion molecules. There are more to it, right? So do we need to always scale up? So we thought about, if these models do have enough expressivity, can we reprogram them? So this kind of, goes back to the cellular reprogramming idea from biology. Basically, our idea is very simple here. Let's take a model from a natural language. And the model is good enough. We just take a pre-trained model that, in this case, a pre-trained supervised model. And then can we reprogram it to learn on, let's say, proteins, and then be able to predict protein properties or be able to generate new protein sequences? So does this even, can it be possible? And we show that, yes, it is possible as long as the pre-trained model in the original domain or source domain is expressive enough. So what we are learning here is trying to map the encodings of the source domain, English in this case, to protein domain, And then we are learning that by having access to a label data set, could be toxicity or could be antimicrobial or could be secondary structure and so on. So basically we are reprogramming a model that already exists in English language, and if you go to Hugging Face or any other repo model zoo these days, you can find many of them. And this is very cheap because we only need to learn the parameters of this matrix called theta. So theta is basically the matrix that is mapping the source encoding to the target space. As you can see, we are approximating VT. VT is the target encodings with the VS, and the theta is the parameters we are learning. So this is a very cheap way to reprogram or fine-tune a model, but from between two different domains.
But
Yes.
where do you get the target encodings from?
Target encodings we are learning.
You're learning.
We are learning the target
You're learning
encode.
theta and VS at the same time.
Sorry?
You're learning theta.
We are learning, yeah. So basically we are using a KSVD. So we are doing a dictionary learning, and we are also learning theta at the same time just by using the loss from how this pre-trained source domain classifier can do on the target domain.
So sorry, to paraphrase. So you're learning the matrix that transforms your embeddings into some embeddings
Yes,
that work really well.
exactly. Yeah, and we are using the loss from the target domain, yeah. The advantage here is that, the model again, here I'm showing you different tasks on protein and peptide domain, like solubility prediction, antibody affinity prediction, and so on. What we see that the model does, the reprogram model does good in terms of accuracy or in terms of regression performance. But so, when we compare to pre-trained model from scratch, the column in the middle, and supervised model from scratch. But what's more important is that we do see that the reprogram model shows a huge amount of data efficiency. So basically, we don't need all of the target domain samples in order to learn, in order for reprogram model to learn. So the reprogram model can learn only with a handful of label samples in the targeted domain. Whereas if we have to do fine-tuning of the pre-trained domain, or if we have to train a supervised model from scratch, we need a lot of amount of label data. We also took it to the sequence design. So here again, we are trying to learn how XT, that is a target domain, can be mapped to a source domain. And we assume that we have an encoder in the source domain that we already have learned. And that could be, in this case, in the natural language, like BERT. And what we are showing here is that how this reprogramming model can be used for, let's say, something like loop design, or in this case, specifically CDR design, in CDR loop design in antibody. So here we are using the mass language model paradigm. Given an English sentence, the model knows how to fill up with English word the mass position. So what we are trying to learn here, two different set of parameters. One is f theta, that takes the target encode target tokens to source token, and f gamma, that takes the source token to target token. And when we learn these two, again using the cross entropy sort of loss, and then we can see that this model can be used for sequence infilling or for loop design. And we don't need, again here we are not using any structural information.
I have a question.
Yes.
When you learn the linear projection, you are taking the 20 tokens from the target
Yes.
to 20 source tokens.
Yeah.
How are those source tokens chosen? Because
So in this case, we were using the alphabets, right? So we were using, and we have also changed the granularity to word. If you go back to the previous case, we were doing a sparse dictionary learning, because in English we have a lot more vocabulary, and in protein we have only 20 amino acids, right? So one way to match up would be if you were going from, let's say, unigram to n-gram in protein domain, right? So then your vocabulary size would be lifted up. Or you can do sparse dictionary learning like we do here to learn a sparse representation of the English tokens. So just some performance, we use the refined GNN benchmark from MIT, who has created a very useful benchmark to compare different designed CDRs using graph neural net models, and also a language model like LSTM. I don't think I will have time to go into the details, but the perplexity model, perplexity PPL here is the naturalness coming from trying to capture the negative log likelihood of a pre-trained language model. RMSD is RMSD. So once we generate the sequence, we have to get to the 3D structure, and then we compare the RMSD of the original sequence versus RMSD of the design sequence. TM score is again the deviation between the predicted structure and actual antibody structure. Diversity, which is very important. We want to show that how many sequences we can generate that are different within themselves when we compare to the ground truth sequence. Because most model, like refined GNN, you can see the diversity-wise, they are very small. So basically, they are good at capturing the ground truth. But when we talk about domain experts, like people who are working in antibody design, they say that, okay, they capturing something close to ground truth, they probably can do with a mutation scanning experiment. But what they want is something that is very different from the original ground truth. Make sure it's diverse enough, so it's worth performing new experiments on top of that. What we do show that reprogram BART, which is more efficient in terms of learning from data, can be quickly fine-tuned or quickly reprogrammed to learn a new task. But it's also important that it also gives us sequences that are consistent structurally and sequentially, but they are diverse enough. And we also showed that if we are using the feedback from a antigen affinity prediction model, as shown here on the bottom right corner, it is possible to design quite a high number of sequences that pass the pre-trained classifier that is predicting the neutralization score of a design sequence. So far I have told you a lot about learning from sequences alone, but should we forget about geometry? The answer is no. It is always important to learn, we can learn always from sequences because that's much more cheap, and we are coming up with more efficient way to learn from sequences. But wherever possible, can we also use geometry? So here I will show you one example where we are trying to augment a smiles-based model with geometric information, but in a cheap manner. So what I'm showing you here is something called tools from topological data analysis. So as we are changing, what we are showing here, how to estimate the barcode. So D is, you can think of like distance, right? So as we are going from small distance to big distance, we are starting to see that some features will be born and some features will die. And some of them would be very persistent. So those are called the persistent features. So you can imagine the small bars will be like noise, right? So they don't matter over time. But the big bars would be, and the ones that do not die, they are like more consistent feature as you try to capture the topological space defined by a geometry. And from this, we can get into the persistent homology diagram, which is basically shows how some of these features can die and as opposed to being born. And from here, you can get to something called persistent homology image or persistent images. And this then can be used by vectorizing on top of a smiles-based generative model. So here we are showing you some example. We are taking a baseline model, which is just learning from smiles to generate new smiles. And what I'm showing you here, that how such models can be augmented if we encode the persistent image on top of the smiles. So what is the advantage here? On the bottom right chart, I show you that how this model, when it is augmented with such persistent homology information, can capture the ring distribution in QM9 dataset. And you can see that sophisticated technique like GSNet, that actually fails to some extent to capture this ring distribution because that requires learning going beyond the next nearest neighbor and so on. So it's very important to learn from this kind of geometric information. And this topological encoding is a useful and efficient way to incorporate such information into the model. And the last thing I wanted to show you, because Cecilia talked a lot about coarse graining. So my PhD also focused a lot on learning to learn how to coarse grain using non-deep learning methods back then. And here in the last couple of minutes, I wanted to tell you that how we are using coarse graining for inverse folding. So basically, given a protein structure, designing new protein sequences that are consistent with the structure. Now, there are many ways you can do that, but again, the problem goes back what I told you in the case of the CDR design. In most cases, these deep neural net-based models, mostly that they use some form of graph neural net, they are good at capturing ground truth sequences, but they are bad at capturing the landscape of sequences that are consistent with that structure. And we thought about it, and we thought one way it would be that let's not provide the structure as a very accurate input to the model, but let's give it as a coarse grain structure. So the way we coarse grain here, as is shown in the figure, that we basically voxelize the space, and then for each voxel we estimate the contribution from all of the residues in terms of the secondary structure propensity. And at the end, you can see on the very right of that figure, we end up with a blurb that has different color that are corresponding to different secondary structure. I think if it's like, you can imagine that if it's red, that means that there is a lot of helical density near that voxel, and if it's green, there is a lot of beta strand density near that voxel. So we give this as an input to the inverse folding model, rather than giving the accurate structure, because our goal is to generate something that is consistent with the structure, but not exactly the ground truth. And once we have designed that structure, that input, that is a coarse grain scale-free input, then we can come up with very sophisticated, some complicated deep learning architecture, which is basically learning to map structure to the sequence. But in this case, because we are giving a coarse grain form of the structure as the input, the model does not just minimize the cross entropy or the loss between the input structure and the ground truth sequence. It now have access to more sequences that are consistent with the input structure. And we compared that with a lot of baseline models that are like, I think one was from Tommy Jacola's lab and several others. One was, I forgot another one. I think it was from Stanford. But what we have found that, of course, as expected, deep learning models are efficient in terms of computation compared to physics-based model like Rosetta design. But also importantly, as we are showing in the right bottom right table here, that the model captures more coverage within each fold, because we are doing folds-based design here. And finally, because we are using a coarse grain input of the structure, this also works where a previously existing model failed because they rely on complete structure input. We can account for low resolution structure, so we can design sequences for, let's say, cryo-EM, which would be much lower resolution, or NMR structural ensemble. Because what an NMR structural ensemble will give us, kind of a fuzzy input, as I showed you here in this chart. So with that, I would just go to my final slide, that we hope that these large pre-trained models, so-called foundation models, are emerging as a promising tool to be integrated in the workflow of molecular prediction and design. It is really important that we don't just take a very machine learning perspective, and this is kind of a reminder to myself because I work in IBM Research AI, and a very few, when we started, a lot of people were just looking at it as learning on images or learning on natural language and forget about the underlying physics. So, and I don't think that's new to this particular audience, but this is something I need to remind my team all the time, that integration of domain knowledge and physics, or evaluating on recovering such knowledge, is very important. Benchmarks and metrics are very good. They are good because a lot of work has been put together. They are good for checking consistency and reproducibility, but they do have limit. Like I mentioned that, ground truth consistency is important as a sanity check, but that's not the end goal as you talk with the domain expert, as they focus more on diverse functional sequences. And I think we are just starting with this emergent behavior with data and neural scaling. Rafa again has a wonderful review on that exact topic. I think we are just starting to see a new paradigm of learning, and I'm very excited to see what it can do in chemistry and biology, because in language is already, in natural language, we do see such model being able to reason, because they were not learned to reason, but they show some reasoning behavior, and I don't know what that would be in case of chemistry and biology. And finally, I think, again, geometry is something that we can never forget, but it's good to know if we need to explicitly model it or implicitly it can be included, and if we need to explicitly include it, in what resolution. So with that, I would thank all my team members at IBM and all my collaborators across different institutes, and thank you all.